this is Mrs. Westmoreland, and here's a video about solution stoichiometry, in particular about calculating concentration of ions in a solution after precipitation has occurred. So we have 80 milliliters of 0.1 molarity silver nitrate mixing with 60 milliliters of 0.1 molarity sodium sulfate. And so the first step is to write the balanced molecular equation for that double replacement reaction, where the silver ion now pairs up with the sulfate ion, and that is an insoluble product, plus 1 silver minus 2 sulfate. And then the sodium ion, which is plus 1, pairs up with the nitrate ion, which is minus 1. So we have a balanced chemical equation where we have 2 moles of aqueous silver nitrate plus 1 mole of aqueous sodium sulfate forms 1 mole of solid silver sulfate, the precipitate, and 2 moles of aqueous sodium nitrate. So the net ionic equation, which is the ions that are involved in forming the precipitation, are 2 moles of silver plus 1 ion combining with 1 mole of sulfate 2 minus ion to make the silver sulfate precipitate, and that of course is our precipitate. So in our particle level diagram, we have one beaker that has the soluble silver nitrate, and those ions are written sort of independently from one another. They are dissociated, floating around in the solution. And we have a separate beaker with the sodium sulfate, again soluble, so the ions are written independently, floating around. And they're in a 2-to-1 ratio, so 2 sodium plus 1 ions for every 1 sulfate 2 minus ion. So when they mix together, the precipitate of silver sulfate is formed, and that would settle out to the bottom of the beaker. The spectator ions, which is the sodium and the nitrate ion, are still suspended in the solution, so they're still written as ions. So when we're trying to find the mass of the precipitate formed, and we have measured amounts of both reactants, we need to treat it as a limiting reactant problem. So we take the volume in liters times the molarity, which is moles per liter, of the silver nitrate to get moles of silver nitrate. Then we use a mole ratio from the coefficients of the balanced chemical equation to compare moles of silver nitrate to moles of silver sulfate. And then we use the molar mass of silver sulfate to find the grams of silver sulfate that would be formed. If all of the silver nitrate was used up, we should get 1.25 grams of silver sulfate. Then we do the same thing with the other reactant. So volume in liters of sodium sulfate times molarity, so 0.100 moles of sodium sulfate for every 1 liter of sodium sulfate. Then we do the mole ratio between sodium sulfate reactant and silver sulfate product, and we use the molar mass of the silver sulfate to get 1.87 grams of silver sulfate if all of the sodium sulfate was used up. So since the answer that I got in my first dimensional analysis is smaller, that means that the silver nitrate runs out first. It's the limiting reactant, and therefore the sodium sulfate would be the excess reactant. So the grams that I got in the first dimensional analysis, the 1.25 grams of silver sulfate, is the true amount of silver sulfate that's formed. So here's the challenging part, is calculating the concentration of each ion remaining in the solution after precipitation is complete. So the way I think about it is I want to calculate first the initial molarity of each of the ions at the instant of mixing. So in that sort of false particle diagram that we did in class, where we're talking about the ions that are mixing together before any precipitation occurs. And to do that, we use the dilution equation, M1V1 is equal to M2V2, where V2 is the total volume of the two solutions that we're combining. So for the silver nitrate, what that means is that we have 80 milliliters of a 0.1 molarity solution that is then mixed and combined together with the 60 milliliters of the other solution for a total solution volume of 140 milliliters. So the new solution, the new concentration of the silver nitrate after those two solutions are combined is the X in this M1V1 equals M2V2, and we get 0.0571 molarity silver nitrate in that instant of mixing. And since we have 1 mole of silver and 1 mole of nitrate for every 1 mole of silver nitrate, it would also be 0.0571 moles of silver ion and 0.0571 molarity for nitrate ion. Same thing works for the sodium sulfate. We have 0.1 molarity solution, 60 milliliters of it, and then it is combined into a new solution volume of 140 milliliters when it mixes with the other solution. So the X is our new solution molarity at that instant of mixing, which we get to be 0.0429 molarity at the instant of mixing. In this compound, since there are 2 moles of sodium for every 1 mole of sulfate, the sodium ion concentration would be 2 times 0.0429, and the sulfate concentration would be just 0.0429 molarity. So down here at the bottom of the page, since the spectator ions do not change in the reaction, the concentration of the spectator ions is the same as that initial, at the instant of mixing, concentration. So the nitrate ion is the same as the concentration of the silver nitrate, 1 mole of nitrate for every 1 mole of silver nitrate, 0.0571 molarity. The sodium ion concentration is 2 times the sodium sulfate concentration, or 0.0858 molarity. So whatever molarity the sodium ion is at that instant of mixing is the same as the sodium ion concentration after. Nothing has changed for those spectator ions. The limiting reactant of the net ionic equation will have a final concentration of 0. So whichever ion is now 100% in the precipitate and has limited the amount of precipitate that has formed will have a final concentration of 0. So if we go back to our limiting reactant problem, since we determined that silver nitrate was the limiting reactant, and indeed in the net ionic equation it is the silver ion that is the limiting reactant, then all of the silver ion will be found in the precipitate in the solid silver sulfate that has precipitated out. So since we determined that the sodium sulfate was excess, there will still be a little bit of sulfate ion remaining after the precipitation occurs because that's the excess reactant. So that is the most challenging ion to find the concentration of. So the spectator ions are the same as their initial concentrations on the instant of mixing using that M1V1 equals M2V2. The limiting reactant, the ion that is entirely in the precipitate that limits the amount of precipitate, is 0. The excess reactant, I do a little table method to find how much is left. So I write my balanced chemical equation and I write my molarities initially of each of the reactants that I found at that instant of mixing. And then this row of my table here is the change that occurs. And so this is where I'm factoring in my mole ratio. So essentially I will use up 2 silver nitrates for every 1 sodium sulfate that I use because that's their mole ratio in the balanced chemical equation. So I've previously determined that the final concentration of the silver nitrate is 0. So I start with a molarity of 0.0571 of silver nitrate. I'm going to use 2x, or 2 moles of that, for every 1 mole of sodium sulfate. And I will end, because it is the limiting reactant, with a 0 concentration of the silver ion. So from that information, I know that whatever I start with, the 0.0571, minus what I've used up is going to be equal to 0, and that allows me to solve for my x. Once I have my x, then I can figure out how much of the excess reactant has been used up, and therefore how much of the excess reactant, and in particular really the excess ion in the precipitate, is remaining. So since I started with 0.0429 molarity of sodium sulfate and I used up 0.026286 molarity of sodium sulfate, that means that after the reaction takes place, after the precipitation occurs, I will still have a molarity of 0.0143 of the sulfate ion after the reaction. We'll talk about this more in class. Thanks for listening.